I just want to have a look at some of the questions I've been sending for homework lately and just to give you some work solutions for them. So the 1998 question 2 in complex numbers. First one was evaluate I to the 1998. To do that, I want to break it down in terms of I squared, because I know I squared is -1. So I'll say that's I squared to the power of 999. -1 to an odd power is always -1. It's a nice mechanical question. Similarly, the next one's quite mechanical, gives us a complex number z, and it asks us to firstly simplify this, which is the same as taking 18 plus 4i and timesing by 3 plus i. So again, nice mechanical process. Calculating that out gives us 54 minus 4 plus 12i plus 18i, and that would be equal to 50 plus 30i. That's leading into the next one where it says express z as a plus ib, so taking it from this form. And so to get z in a plus ib form, I want to take 18 plus 4i over 3 minus I, and I'm going to realise the denominator, so I want to multiply numerator and denominator by the conjugate. I've already worked out the new numerator, that's 50 plus 30i, and the numerator is going to work out to be 10. So I get 5 plus 3i in a plus ib form. Great. Hence, otherwise find the modulus of z. Well, this is easy to find the modulus of z of. We just use the fact that it's going to be equal to the square root of 5 squared plus 3 squared. So we get root 34. The argument of z is going to be given by is theta, and what we're going to have here is we're going to have that tan theta is equal to 3 on 5. And just using our calculators, we get that in radians as theta is equal to 0.54 radians for the argument. So that was again very mechanical. Next one is sketching a region in the complex plane. Now, a suggestion if you're stuck on this sort of thing, so it's the modulus of z minus 2 plus I is less than or equal to 2. A suggestion is you could do it algebraically. You could work through and say that z is x plus iy, so I'll write that as x minus 2 as the real part, plus y plus 1, I as the imaginary part, less than or equal to 2. Algebraically, work through it. Modulus is the square root of all that, the real part squared plus the imaginary part squared. I'm not going to want the square root to hang around, so I'm going to square both sides and get it like that. And that'll tell me that I've got a circle radius 2. So at the centre is at 2, -1, and the radius is equal to 2 for that circle. And because it's less than, it will be all of the area enclosed within that circle that I'm interested in here as my region. Now the other region was given to us by the imaginary part of z is greater than or equal to 0. The imaginary part of z is just y, so it's y greater than or equal to 0. So combining those two regions on here, I have a circle whose centre is 2, -1. Radius is at 2, so it's going to look something like this. The region inside is what I'm interested in, and then I'm saying y is greater than 0. So all up, I'm after this region here. Now I did say there was another way to do this modulus one, modulus of z minus 2 plus I. Rather than going through the algebraic process of trying to use the modulus formula, you can actually do it as a recognition step. And the recognition step says, well, I've got the modulus of z minus brackets 2 minus I, less than or equal to 2. And straight away I can recognise that as a circle, centre 2, -1, radius 2. So in general, the modulus of z minus a plus ib less than or equal to r, that's a circle. Centre is at AB and radius equal to r. So that's a nice little easy way of doing it without having to get into all the algebra. Right, the next part had an Argand diagram question. It was looking at the relationship between the complex numbers, and the points were z, this was the vector z, and this was the vector w. And it was saying that the 2 points here, the triangles are isosceles, they're equal to the same, so therefore the fact that it's isosceles tells me that the modulus of z is equal to the modulus of w. They're both the same length. POQ is a right angle, and the right angle here means that therefore w must be equal to IZ. They're both the same length, and it's been rotated 90 degrees. That's the same as multiplication by I. So to show z squared plus w squared equals 0, what I really have when I have z squared plus w squared is z squared plus IZ squared, which we know I squared is -1, so I get that as equal to 0. That's a nice easy one, just testing your understanding of a few of the geometrical properties on the Argand diagram. Last question is a question I really like. By solving the equation z cubed plus 1 equals 0, find 3 cube roots of -1. So that's not too bad. We can do that by simply establishing that if z cubed plus 1 equals 0, then z cubed equals -1, so therefore z equals -1 is a solution. And once I have one solution, I know that the remaining solutions are equally spaced around the unit circle here. So my first starting point is here. I need to get these other two solutions to make this equally spaced. So this angle back here must be 2 pi on 3. This angle here then is pi on 3. So I have cosine pi on 3 as one solution. Similarly down here, I'll have cosine -pi on 3. So my roots z1 is equal to -1, z2 is equal to cosine pi on 3, and z3 equals cosine -pi on 3. The next two parts of the question I really liked. Let lambda be a cube root of -1, where lambda is not real. Show lambda squared is equal to lambda minus 1. So I want to show that lambda squared is equal to lambda minus 1. Now I know that lambda cubed plus 1 is equal to 0, because it's one of the roots, just not the real root. I can factorise this using the sum of cubes. Now, lambda is not real. So therefore, lambda does not equal -1. So therefore, lambda is not the root to this one, lambda is the root to this one. So therefore, lambda squared minus lambda plus 1 must equal 0. So therefore, lambda squared is equal to lambda minus 1. So that's quite a neat little application there. The next part, again very neat, hence simplify 1 minus lambda to the 6. So I've got 1 minus lambda to the power of 6. Well, that's equal to negative lambda minus 1 to the power of 6, which is equal to negative lambda squared to the power of 6. Now, raise it to an even power, get a positive. That gives me lambda to the power of 12. Lambda to the power of 12, well, one of the things I know is that lambda cubed has to equal -1. So that can actually be written as lambda cubed all to the power of 4, which is -1 to the 4, whose answer becomes 1. Nice and neat.